Before we start, how's everyone feeling? Are we feeling pumped? Yeah? Saturday, could be sleeping in. Decided to come some big data talk. So that's pretty amazing. It's quite a full room. So I hope you don't mind. I'm just going to take a photo. Just look at the camera. That's all right. I'll go that way. All right. Can you guys put your hands in the air if that's all right? Yeah? Hello? Yes? Amazing. Amazing. Saturday morning fun. Who came to my workshop yesterday? Some of you came. Raise your hand. A few? OK. Who is using Spark at work? OK. Python? Yeah? OK, that's good. Who is maybe working with data on a day-to-day around gigabyte of information? Yeah. Above that, anybody? Terabytes? Ah, cool. Because usually, as a data scientist, you kind of don't work with terabytes of data, right? So I'm always curious, like, is this actually a problem that people have? And it turns out it is. And that's what this talk is about. So are there different kinds of file formats that are more suitable for larger quantity of information? So that's what we're going to focus on in this talk. So I know everyone's favorite. What's your name? Robert. It's great, because I can just read it. How are you doing, Robert? Are you good?
Yeah, good, thank you.
Do you like CSV files? There's only 3 answers.
Don't know.
You don't know? All right. Well, if you can stay away from them, then you have a better time. So, as a data scientist, this is the things that you see on a day-to-day. CSV, the lingua franca of pandas tutorials. Then we've got JSON. And in the previous talk, gentleman was talking about the difference between data scientists and software engineers. And JSON is a file format that is really used for communicating amongst web services. So it's probably more on the engineering side. But it is a very common file format. Now, I'm really, really sorry. I don't want to bring bad memories to some of you that use Java or come from the enterprise world. But XML is still a thing. It's still a thing, so lots of markups everywhere. It's great if you're paid by lines of XML that you write, because it gets really long. But quite an impractical file format. And just to make sure everyone is on the same page, I've got various files I'm going to use in this talk, just to kind of showcase the benefits of using big data file formats. So first of all, I'm going to have this CSV file here. It's London. It's finance, so we're going to have some loans here. So CSV file that represents how we issue loans, with interest rated to the customer. And I also have a larger kind of a JSON file here that I'm going to use. It's a sample of the Open Library database, books that are published in the world. So what's really useful with a file format, the definition of file format, is it provides a common interface for different application of services to be able to read and understand this information. So using a tool like Pandas, for example, Pandas will know how a CSV file is structured. We'll be able to read from that file and represent it in the internal Pandas data frame. So this is how we could visualize this CSV file here, right? So we can see the loan amount, the interest rate, etc. And now that we've got this Pandas object, which is still backed up by this CSV file, then we can run a bunch of other queries like describing a specific column, right? So that's a real benefit with a file format. There's a common understanding of how it's structured, and different applications or different libraries can read from that file format. It's a similar story with JSON. So again, here, let's use Pandas. What we're going to say here is, well, read up this JSON file where each line is represented as a JSON record. Okay? So instead of having one gigantic curly brace at the top and bottom with a bunch of things, each line is a series of curly brace, right, in the JSON representation. And here again, a completely different file format, but Pandas understands it, and we're able to read the data. Okay? Now, as I showed it here, if I do another, you'll see we've got 400 megabyte here for the loan CSV file, and we have 100 megabyte for the JSON file. Now, this might be the sort of data that you deal with as a data scientist, right? Here's a sample of the data. Let's do some exploratory data analysis. Let's maybe train a model to do some prediction. But what about big data, right? Like, what about if we had 100 gigabyte of data? Clearly, here, you already saw that even loading this file took a bit of time, even on my laptop. There's quite a reasonable MacBook Pro here. So are these file formats suitable for big data processing? That's the kind of question that we'd like to have an answer for. So let's conduct an experiment. So what I've done here is I've uploaded a larger data file here. That is 92 gigabyte. Okay, so this is sitting on Amazon S3. So that's a cloud service where you can store data up to 5 terabyte per file. Okay, so let's just use that to do some data processing using the tools that we know. So in order to do that, I set up a cluster of machines. So I've got 16 machines here that are going to do some work for me. Okay, and this is using a service called EMR, which stands for Elastic MapReduce. So essentially an easy way to set up a cluster of machine that's configured with a software stack. So in my case, I'm going to use Spark, which is a data processing engine, which distributes the works on different machines. Okay, and then I can aggregate the result. So to do this, what I've done here is to write a bit of Spark code in a notebook called Zeppelin. So it's very similar to Jupyter, just a different UI, really, and a couple of interactive data visualization features. And the first query here, and I'm going to describe what's going on, and hopefully everyone is happy with that. But what we're saying here is load up this file from this S3 bucket. So that's my kind of 100 gigabyte file. And it's JSON. Okay, so it's one big JSON file. What we're going to say is, well, parse those entries, and then find me all those books where Cambridge is in the title. And I just want to count those. Okay? So that's kind of like interesting query. I just want to find out whether Cambridge is an interesting word that people use in book titles. So if I launch this query, what we're going to see is that it's already taking a bit of time. Okay? So Robert, how much time have you got? How's this Saturday going? It's going all right. Is it getting better and better by the minute? Excellent. So the point here with this demo is you can see things are starting, but it's going to take a long time. So the real answer, this is probably going to take 5 minutes using 16 machines that are trying to process 100 gigabyte of data together. So by the end of this talk, I'm going to show you how we can go from 5 minutes to around 20 to 30 seconds, just by embracing a different file format. Okay? We're not going to do a lot of change to the code that we write. We're just going to convert this file into a different representation in order to get querying benefits. Okay? Now, the bigger picture here is, especially with cloud computing, you might think, oh, it's really cheap to kind of use lots of machines and store a ton of data. That is correct. It's cheaper. But the more data you store, the more you're going to have to pay anyway, right? So, if you got delicious AWS credits, it's fine. But you're going to run out. And so there are benefits on being able to compress and encode this data so you reduce the size. And that's a clear business value that you can add, right? So if you can save money and get the same result quicker, sounds like a pretty good win to me. Okay, so that's what this talk is about, is how can we get those benefits. So it's still running, so let's see later on what we've got. Okay, so that's the motivation for this talk. Are there different sort of file formats? So CSV clearly has benefits. It's simple and it's human readable. If I give you a CSV file, you can immediately read it. Now, unfortunately, it's not space efficient, especially for kind of hierarchical data when you've got one-to-many relationships, or a customer who have several transactions. How do you model that into a CSV table? You're going to have some repetition, right? Maybe the customer ID or something. And it's very limited in terms of constructs available. And this is where JSON kind of attempts at fixing some of those issues. It's still human readable. If I look at a structure, I can see the attribute, I can see its value. You can have nested hierarchies, so that's a deficiency with the CSV format that is solved with JSON. Unfortunately, it's still not mega super space efficient, right? Because if I want to have several customers, I'm going to have to repeat the attributes. I'm going to say, this is the name of Robert. This is the name of the gentleman over there, right? So you have to repeat that to get a nice human readability property. So a bit of a downer. So can we improve the situation? Now, the problem with traditional file format really stems from how hardware and communication works. So these are numbers that are taken from a presentation from Jeff Dean. He's like the god of distributed systems. He works at Google. He pretty much invented the whole distributed system stack at Google. So he's a clever man. And this is kind of some of the numbers he pulled out. So he was arguing that the problem we have today is not so much the CPU, so kind of the unit that's going to process that data, right? When you train the model, the CPU is going to do some work here. The real problem is the data that we have to load. So on the very top, we've got the level 1 cache. So cache is a bit of memory that is sitting really close to the CPU. So the CPU can kind of say, hey, give me some data so I can process it in my registers. Okay? And that access is really, really fast, okay, with sub-nanoseconds. Now, unfortunately, there's a limited amount of cache memory that you can have because it costs more to have this really fast kind of memory. Okay? So there's hardware limitations there. Now, the next best thing that you can get is the main memory. Okay? So the RAM. So typically here on my laptop, I've got 16 gigabytes of RAM. But my cache will have like 64 megabytes. Okay? So that's kind of quite a big difference here. And now suddenly we're talking about an order of magnitude higher just to be able to load some of the data so the CPU can do some work, right? So in practice, what's going to happen is you're going to load memory from the main memory. It's going to sit in the cache, and then the CPU will read it off from the cache because it's really fast to access, especially if you need to read it multiple times, okay? Now, things get worse and worse, okay? Next thing is the SSD. So we've got some flash storage. I can store the data, but it's going to be even slower just to read that information in comparison to the main memory. And it's not even any point talking about hard disk and all those things that are really old now, right? But they're even slower. Now, the worst of this whole diagram here is the network traffic. So if we think about a big data system where we've got a cluster of machines that are trying to coordinate their work together to give you an answer for a query, you're going to have to exchange a lot of data, right? So I'm going to get Robert involved here, and we're going to do some work together. I'm going to text you, call you. That's really expensive. And in terms of latency, suddenly we're talking about milliseconds, okay? So there are clear benefits on reducing the data size from a performance point of view. We can get the CPU to do work, but the CPU still needs to load that data so it can do work, and that's where the bottleneck is, okay? So another interesting graph here shows kind of like the comparable performance increase over time of the CPU versus the main memory. And what we can see here is that the memory kind of evolution over time goes at a way slower rate in comparison to the CPU. So the memory is the bottleneck. That's where we need to pay attention if we want to be able to perform work quicker. Okay? So what are the goals with big data file formats? Well, ultimately, there's two things that we really want. Right? One is querying efficiency. So can we come up with an alternative layout? Can we shuffle how information is represented in a file to be able to answer certain kind of queries in a fast manner? Okay? So that's the question that we like to solve. Now, the other one is space efficiency, Robert. Right? So if we can reduce the information, then we can load it quicker. Okay? So let's run through an example of how this may work. So I've got some Tableau data here that represents some loans that we are issuing. So those are probably not great loans because the interest rate is really high. But what you have here is a column that represents the loan ID. You've got a column that represents the interest rate, then the amount, and then the term for that loan. Okay? So here is something that looks like a CSV file. And the question is, how can we translate this data so we can store it to disk? Okay, so what's the translation mechanism from this pretty table to bytes? That's ultimately what we need to come up with, because bytes is the only thing that computers can work with, right? 1 and 0. So how do we go from that to 1s and 0s? Now, there's several strategies. And different strategies will have different trade-offs. So probably the one that we are the most familiar with is the row layout. So it's the idea that let's take that tabular data and we're going to encode that information. So we're going to encode the number, the ID, into bits. We're going to encode the string with the term length into bits as well. And we're going to append that one after the other one, right? So we get a sequence of bytes. So that's one approach, the row layout. Now, this is really useful for these kind of queries where we say, hey, I want all the information for a specific object that has an ID. And the reason it's really useful has to do with another hardware property called spatial locality. It's the idea that the computer, when you read memory, it's not reading just one byte at a time. It's reading a whole row of information. Okay? So one read will give you a whole series of bytes. Okay? So in this case, hey, if I'm able to scan through this data and find the ID equals 2, then with one single read, I get the whole information loaded in main memory. So that's really cheap and efficient. And there's another useful property whereby the cache will often prefetch more memory because it can predict what's your data access. So you'll read off the ID 3 as well and load in memory because your code, it feels like it's going to use all that information. Okay? So being able to have all that data one after the other is really useful because it's preloaded. Now, an alternative layout is where we reshuffle things a little bit, is by saying, well, instead of having each object one after the other one, is we actually take all of those same attributes and store them one after the other one. Okay, so this is called a column layout, because if you think about a traditional table, like I had here, what I'm doing is, instead of appending one row after the other, I'm saying, take that, and then append that, and then append the other column, right? So this is just reshuffling the way the data is encoded in bytes. Now, this query here, which is a realistic query that a web application would have to perform, right? If we are trying to log in a user and his ID is 2 and I want to find the loans, this kind of stuff that you have to do. Suddenly it's going to suck because all the information is not available right after the other one. I'm going to have to do a scan here to locate the ID2, then I'm going to have to figure out what the rest of the data is. So we're going to have to do multiple reads in order to collect this information, because it's scattered across the memory. Okay? So this is really sucky. Now, is that bad, though? Is that the kind of queries that we do as a data scientist? This is the kind of queries that web services, web application often perform. As a data scientist, usually what you want to do is to aggregate data with specific columns, doing something like a sum, the average, finding some statistical information. Typically, you don't need all the attributes of an object. You're selecting a few of them. So here's the kind of query that we might be interested in doing, right? So as a business, how much money am I lending? What's kind of my profile today? So we're going to select sum for the amounts. Okay? Now, the row layout suddenly doesn't perform very well, right? Because if I want to find the amounts, I'm going to locate where each amount is. And they're not right after the other one, so multiple reads are required. And that needs to be loaded in the memory. If you remember, you're paying this cost every time. You're paying the cost from this to memory, from memory to cache, and then the cache is being read from the CPU. So ideally, we'd want to reduce the number of reads that we have to perform. If the data was one after the other one, it'd be great, because in one go, it's loaded. And this is really where the column layout shines, right? In this case here, if you want to calculate the sum of the amounts, with one single read, the information is there, it's already loaded, the CPU can go and do the work, okay? So that's kind of like the two big file formats. And there's trade-offs, right? No one is advocating that one is better than the other one. It really depends on your scenario and your situation. As you saw, the row layout is really useful when you want all the attributes of an object. That's great, select all kind of queries. But the column layout is going to perform better for more kind of business intelligence queries where you have to perform arithmetic on a subset of columns. Okay? And there's other benefits by using the column layout is that the data is a lot more homogeneous. Right? If you think about the row layout, I've got an ID, which is a number. the thing that follows is a string, and then it's a number, and then it's another string. It's really more challenging to be able to encode and compress this data. If you know that all of that data is the same type, you might get better compression ratio. So if you think about a timestamp, which is a number, and you've got incremental timestamps, potentially we could just store the delta of that timestamp inside of the whole information. That's kind of stuff that's possible when you know that you have a sequence of data that is of the same type. Okay, so that's an added benefit with the column layout. So that's kind of like the intuitions and the concepts. So what exactly is a big data file format? It's got big data on top of it, so it is cool. What does it mean? So it's generally the idea that we have a specification for representing information, right? That is really suited for storing large information. And it would sit on top of an existing file system, right? So it's just a file format specification. It's not a implementation like the Hadoop file system would be, right? So you'd be storing maybe Parquet, which is a big data file format I'll mention in a second, on top of something like HDFS, okay? So it's supported by different execution engines. So Spark, that I demonstrated just earlier, has support for Parquet. There is the PyArrow project in Python that has an in-memory representation for columnar layout. I'll talk about that as well. So there is wider adoption for existing big data file formats. And the two big ones that you often hear are Avro and Parquet. Now, Parquet is the cooler one because it's a French word. Has a good ring to it. With Avro, I'm still not sure what does that mean. But there you go. So Avro is a raw layout. Okay. But it's really a wider ecosystem. It's kind of used for RPC, where you want to serialize data so that another web service can read off that data. So when you're streaming a sequence of bytes, that's what Arrow is really useful for. And it comes with a set of tools to implement this RPC mechanism for you. Okay? So what I mean by RPC is remote procedure call, right? So I'm making a request to Robert here. We're going to have to exchange some information. You're going to give me a result. So somehow we need a way to serialize the information so we both understand it, right? So we'll serialize that using a row layout. Now, Parquet is a columnar layout that has also support for metadata. So not only would it store the information in a column layout, you can still provide information like, what's the maximum element in a group of rows? Or what's the minimum? And that might influence the querying efficiency of some queries. Okay? So there's that flexibility. Right, let's do a little quiz. The first one. If we have analytical type of query where we use a subset of column and we want to do something like a grouping by, what would be a suitable file format? Parquet or Avro or row versus column? Come on, someone. Parquet. All right, so columnar layout, because it's business kind of intelligence queries where we want a subset of columns and they'll be stored one after the other one, so really efficient to work with. And the last one, load up all data for a specific timestamp range. Avro, right? So we want all the information, and it'll be encoded one after the other one. So it'll be a lot cheaper to use a row layout. Awesome. So here's a complicated diagram, which is unreadable. Awesome. But this gives you an indication of how the Parquet file layout is structured. So there is, on the right-hand side here, you'll see metadata. So that's additional space where we can store information. So something like the Spark engine could read that metadata to do a bit of optimization on the query. On the left-hand side, you can see how the information would be structured. So Parquet uses the terminology of a group. So we'll have a row group that has multiple columns. And that group of rows could have metadata associated to it. That would say, for example, the maximum customer ID that we've got here is 40,000. So if I want to do a select that says the ID greater than 50,000, the whole thing can be skipped. There's no need to look at it because the metadata already tells us that actually we're not going to find anything in this range. There's no point even scanning the whole thing, right? So for that to happen, we need a way to store this metadata. So Parquet supports that. But we need the engine to be able to understand that and read that information, and then we'll optimize the runtime execution of that query. And now it's also got columns, and columns will also have some metadata that could also be used for querying efficiency. So there's two classes of optimizations that are possible by using this kind of layout. The first one, which sounds really fancy, great for dinner parties. Robert, this one is one to use. Predicate Pushdown. And it's the idea that by storing, like I said, information at the file level, metadata, then the engine could filter out some of the data. We don't need to scan it because we know it's irrelevant already, right? So if we want to find things that are greater or smaller, if the metadata already tells us the range of information available, then we could filter that out, right? So that's the idea of a predicate pushdown. Now, projection pushdown is the idea that given that the columns are stored one after the other one, then we don't need to read unnecessary columns, right? So if you think about a row layout where you have to read everything, you're going to have to one by one decide which column you choose, right? But you're still scanning everything, and then you're filtering that out to aggregate the subset. The projection pushdown says, well, given the columns information are right after the other one, we don't need to scan that, right? So that's the benefit that you get. So let's take a query like that, right? Select name and state from customers where the ad is greater than 10,000 and below 40,000. Well, thanks to predicate pushdown, we can already focus on those groups that are inside that range, right? So if a row group says, hey, the information container is greater than 50,000, then it's kept, okay? So that's the idea with predicate pushdown. And then with projection pushdown, we can just select those two columns that we're interested in because all that data is sequential one after the other one, okay? Awesome. So that's the querying side. So that's one of the concerns. How can we get the job done quicker using a different layout? Now, the other side of the story that I mentioned earlier was, what about space efficiency? Are there mechanisms so we can encode the data whereby it's nice, we get the querying efficiency, but we reduce the space? And the trade-off is we know that it's OK to tell the CPU to do more work because that's cheaper than loading data from memory. Okay? So that's the trade-off we've just decided is let's put more work on the CPU to decode information because we know it's cheaper to load it anyway. So that's the key intuition. And there's different tricks available to encode data. So let's go back to a notebook. And those are kind of encoding mechanisms that would be supported by Parquet. Okay? So the first one I'm going to talk about is called dictionary encoding. So let's say I've got it's really useful for the scenarios where you've got a lot of repeated symbols. So for example, our favorite programming language. Guess what's the odd one out here in this list? If you can stay away from JavaScript, I recommend. It's always tricky. Although things have gotten better, I guess, with like ECMAScript 6. But. So here's the idea. We've got a bunch of names, so Raoul, Olivia, Thibault, Kevin, etc. And here's our favorite programming languages, and this is the postcodes where we live. As you can see, there's repeated information here. Python, here's the winner. It's repeated quite a lot. The CB1 and CB4 postcode are repeated a lot. So can we come up with an alternative representation whereby each of the symbol is smaller, and because we know it's repeated, we might get some benefits, right, by encoding that. So here's some code that I've written for the purpose of this talk. And the first phase here is to generate tokens for each of these symbols. So something like Python, has 6 characters. Oh my God, right? Well, we could represent that using a number or even kind of a bit encoding, which would be even more efficient, right? And now that I've got this dictionary, which you need to store, right? So this is trade-off that we need to generate that. That's going to take memory. That's going to take space. But if we have a lot of repeated symbols, if Python occurs 1 million times in my data set, then I will be able to reduce the size. And the encoding mechanism just says then replace of these repeated symbol with the associated token from the dictionary. Okay? So as you can see, just visually, this representation here is more compact in comparison to using those repeated strings here. So that's one encoding. It's called dictionary encoding. Now, another encoding which shines in situation where you have not only repeated symbols, but they are one after the other one. Okay? So there's a difference between repeated data that's kind of available everywhere in your data, but there's also data that is sequentially repeated. Okay? So here I've got numbers here. For 5, you can see is repeated quite a few times. I've got 0. So those might be things like different events that are triggered associated to a tag that would be repeated. And by using a mechanism called run length encoding, what we can say here is, well, why don't we store that event or that number or that symbol, and next follows how many times it occurs. Okay? So in this case here, 5, you can see occurs 4 times. Okay? So let's store 5 and 4. 0 occurs 1. So you can see that actually for 0, we've lost a little bit here, right? Because suddenly we have to store the information twice. We have to say 0 occurs 1 instead of just saying 0. But for scenarios where the data is repeated sequentially, then we definitely get benefits. And the trade-off here is that the CPU will have to unravel this data. But you can't do it because it's readily available. And it's cheaper to get a CPU to do work than to load up tons of data in memory. Now, another encoding mechanism is called bit packing. And this one really makes me sad. So, you know, storing the number 1 takes so much space. So I've got a 64-bit architecture here. This is how you store 1. Think about it. So what bit packing says is, well, if we know that the range of those numbers have a fixed size, you know, for example, they would be between 0 and 100, then you don't need 64 bits to store numbers between 0 and 100. Okay? So for example, here we can say, well, to store 1, we're just going to allocate 5 bits. Okay? So the question is, well, how can we use this when we've got, for example, a list of numbers that might representing transactions? So using the normal way of doing things, so this is the 64-bit version, this is how much space this is taking in the memory. Okay? If we use a 5-bit encoding, then suddenly things are more compact, because we would have kind of the first 5-bit here represent 1, and then this would represent 5, you know, and suddenly the data becomes more compact and efficient. Okay? So that's particularly useful when you already have some knowledge about your domain and you know that the range of this data is going to be restricted. Now, finally, the last one I want to talk about, which I mentioned a little bit earlier, is the delta encoding. So if we take this, this code here where we've got timestamps, so that might be stock text, for example, right? You know that they actually executed like one after the other one. Then instead of storing that representation of that timestamp, what we could do is to store the delta, because we have the domain knowledge here that actually the data is incrementable. Okay? So here we store the initial value together with the increment based on the predecessor. And that's another way to make the data more compact, which will lead to space efficiency. Cool. So those are examples of encoding that Parquet supports. If you're interested in working with Parquet, there's different ways of doing this. There's this PyArrow project, which is fairly recent, but it's becoming really interesting. So, you know, Parquet is the file representation of the data. So how do we encode it to bytes? So it's stored on a hard disk. Arrow is how do we encode this data in memory? Okay? So we need a columnar layout that sits in the memory, that is cache-friendly. And that's the Arrow project. It's trying to tackle that issue. Because eventually the data that you have here, you need to load it so the CPU can work on it. So Arrow kind of bridges that gap. So just to give you a couple of ideas how you can work with this. So here I've got a bunch of dependencies to load. And I'll make this notebook available after this talk in case you want to run through it. So the first thing I'm going to do here is, given my pandas data frame about loans, which I loaded earlier, I'm going to store this into a Parquet file. And then I'm going to read this Parquet file here and encode it to another pandas data frame. So as you can see here, this is our friend pandas, but we are reading data from this Parquet file using the Arrow project, which has an efficient representation of this information, and then we can still use pandas to query that, but that'll be more efficient. Okay. Now, on top of encoding, Parquet also comes with support for compression mechanisms. So we could use something like gzip or snappy. Different compression algorithms have different trade-offs in terms of CPU cost versus space cost. So here to give you an example of gzip. So you see, it takes a bit of time because that's essentially lots of CPU work. And again, we're able to use pandas. Now, here you can see the benefits, right? So here's a launch file stored as a CSV file. Here is Parquet using those encoding tracks. And here's Parquet with encoding plus compression, where now it's 71 megabyte. So we've gone from 400 to 71 megabyte here, okay, just by leveraging this alternative file format. Now, that's if you want to work with Parquet in Python. There is a tool called Parquet Tools, which allows you to debug or kind of understand how those files are structured. So if I look at loan compressed, it's a binary file, right? It's tons of bytes, so it's not particularly friendly. So with Parquet Tools, what we can say, for example, is I'm going to say head and then loan compressed Parquet, and then less. And then here's the information, right, in human readable format. So it's quite a useful tool to kind of inspect a file that might be sitting on, on some sort of cloud storage. So I could find, for example, some metadata information here. And you'll see all this weird stuff here is essentially type information from pandas, so that when it's read again, we already know what's the sort of data that we're working with. Okay? So that's a good, useful tool to look at. Now, at the beginning of this talk, I was saying, if we use a JSON big file, and even if we use a cluster machine, even if we use Spark, things are slow, and things take a lot of space. So how can we leverage Parquet now together with Spark to improve the situation? So what I've done is, before coming here, is to essentially encode this big JSON file into its Parquet representation. And suddenly, it's around 11 gigabytes of data. Okay, so we went from 100 to 11 gigabytes. So already you can save money for somehow, right? For the business case, this is a great case. Is we can save money by using this alternative file format. Now the other question is, well, is the querying going to be any better? So as you can see, the previous query here used the Spark RDD API, and what we're saying is, parse this JSON. Count those books where Cambridge is in title, and this is loaded from this S3 bucket. And it took around 4 minutes to execute. So let's see how this one performs. So I'm going to do what this is going there. I'm going to see how the cluster usage is doing. OK. So there's a bit of a peak of work here because I was setting stuff up before the coming here. Let's see if we got another peak coming. Right, so you can see this little thing here that's basically saying, hey, we suddenly decided to do some work in my cluster. So hopefully it's going to keep on increasing. And the result is finished. So it took 33 seconds, okay, as opposed to 4 minutes, and we get the same result. Okay. So hopefully, after this talk, kind of the main takeaways is it's not just about CSV and JSON. It's really useful if you have to work on some sample data, figure out what the right query is. But suddenly, as you need to scale to terabytes of information, and some of you raised your hand saying these are kind of real problems you have, then adopting a big data file format has tangible benefits, both in terms of space efficiency and reducing the storage cost, but also in terms of querying efficiency, so you get your result quicker, specifically for business intelligent types of queries, right? This is where Parquet is really useful. Now, there's a ton of other stuff going on in this space, so it's still kind of a space that is in development. So I've put a few links here. There's different benchmarks that compare different file formats. AWS shows some benchmarks as well by storing terabytes of data using Parquet, as opposed to something like CSV, and the benefits are clear and obvious. And there's a couple of new developments happening. So there's a few open issues with Parquet. One of them is to add support for Bloom filters to do faster membership access as well. So this is kind of stuff that would be stored as metadata so that engine could read that information. So lots of stuff going on. So to conclude, hopefully some of you will take a look at Parquet and Spark. And it's widely adopted, so many companies that we worked with at Cambridge Spark are using Parquet, especially big banks, because there's a ton of data to process. Cool. So before I wrap up, I just want to mention Cambridge Spark. We have a stand over there, so we're going to stick around. So if you're interested in talking to us, come say hi. I hear the gentleman in previous talk mentioned us, actually. It's pretty cool. So we run a bootcamp, so we're not the academic, theoretical kind of programs. We're more the kind of hands-on data science curriculum, which merge actually more software engineering practices, like unit testing, code styling, code convention. Things are really important to maintain code, and that's what we focus on. But we're very much a complete data science curriculum, so we cover things like unsupervised learning, clustering, but different ways of doing supervised learning with categorical data and regression models as well. We would talk about things like big data system and Parquet and how do you optimize that. I think some of the students are here. Is anyone? Let's see, Tola. Amazing. She's one of our students. So you can talk to her as well to see what she thinks about a program rather than just hear from me. So thanks a lot for coming to this talk. And see you around. I don't know what I've done, but
Thank you very much for your time and your presentation.